some properties of equality that you maybe heard of and use in algebra 1. Okay, we essentially use these properties to help us solve equations. So, the first property we're going to talk about is the addition property. And that, all that says is if you have an equation A equals B, you can add the same exact thing on both sides. You're allowed to, and that's called the addition property of equality, adding the same thing on both sides of the equation. Okay? The subtraction property of equality, what do you think we're going to do for the subtraction property of equality? Yeah, we can subtract the same thing on both sides using the subtraction property of equality. Because when you're doing the same thing on both sides, that equation is so true. The equation, both sides are so equal to each other. Okay? What do you think we're going to do with the multiplication property of equality? Yeah, we're just going to multiply the same thing on both sides. And it's still true. Multiplication property of equality allows us to multiply the same thing on both sides. And then with the division property, we can divide the same thing on both sides and it will still be true. Okay. This allows us to do the same thing on both sides of an equation. Okay. The distributive property, again, you used it in algebra 1, allows us to take this A and distribute it to everything inside those parentheses to get A times B plus A times C. Whenever you combine like terms, that's a part of the distributive. So if you're ever combining like terms in a proof, you're using the distributive property. Go cite them. Substitution property says if A is equal to B, then either A or B may be substituted for the other in the equation. In other words, that's like plugging something in. So if you're told x equals 5, and then you take 5 in and plug it into x in the equation, that's substitution. Okay? I like to think of substitution as being replaced. So you either replace something or you plug something in. That's how I like to think of substitution. If I'm gone, a substitute replaces me. So that's how I like to think of substitution. Something's being replaced or plugged in. Questions over those. Those are things that you talked about in algebra 1. Okay, the properties of equality. We essentially use them to solve. I have something in my eye. Sorry, probably making really weird faces. Okay, now we're good. We use them essentially to solve equations. But there are some properties that we use mainly for geometry purposes. And there are more properties of equality, but they're more from geometry. The first one is the reflexive property, and all that means is A is equal to itself. How I like to remember the reflexive property? Reflexive sounds like reflection. And when you're looking at a mirror, you are looking at your identical image, yourself. Okay? So whenever you have something equal to itself, the same things on both sides of the equal sign, it's the reflexive property. Okay? Circle and star this guy. We use this a ton. Okay? We use this a ton. Symmetric property we don't use a whole lot, but it's just something good to mention. Reflexive property says if A equals B, then B equals A. You just flip it. And that's true. Okay, we don't use it a ton. But it is something good to mention just because it doesn't come out. And then the last one's called the transitive property. And that says if A equals B and B equals C, then A also equals C. Because if A and B are the same, and B is equal to something else, then A is also equal to that something else. Okay? I would circle and star this one. We use this one a ton in geometry. Reflexive property and transitive property we use a ton of. Okay? properties of congruence, they're the same exact thing, but instead of having an equal sign, there's a congruent symbol. So it would be A is congruent to itself, A. If A is congruent to B, then B is congruent to A. And if A is congruent to B, and B is congruent to C, then A is also going to be congruent to C. It's the same exact concept, except a different symbol. Questions on that? So these are just some basic properties that we're going to use throughout this. So now what we're going to do is just look at some algebraic proofs. Again, this is something I'm not testing you on. You're not going to have a quiz over. You're not going to do it on your OST. Okay? But it's just something to help you get the flow of a proof down. Okay? Because essentially what you do in a proof is you have a bunch of statements, which I like to think of are steps, and then reasons why you did that. Okay? And we get a good idea of how that works with algebraic proofs. So they're really nice on these first two examples. You have all the statements or all the steps. Okay? So we're given an equation and we're solving for x. We just have to figure out, well, what property, what reason did we use to do that step? So we take a look from 1 to 2. What happened in the equation? From 1 to 2, what happened? We didn't combine their terms. What changed? Yeah, we got rid of the 8x. How did we get rid of it? Yeah, we subtracted it on both sides, meaning we use, I heard someone say it, we use the subtraction property. Now you can abbreviate property. I like to, we'll abbreviate a lot in here with proofs. So to go from step 1 to step 2, we use the subtraction property. So we were able to write step 2 because of the subtraction property. So that's why subtraction property goes with step 2. Then from step 2 to step 3, what happened? What changed? Yeah, we used that subtraction property again, and we subtracted 9 on both sides. So when we do that, subtract the same thing on both sides, we use the subtraction property. And again, we use the subtraction property to get statement 3, so that's going to go with statement 3. And yes, you are allowed to use the same reason more than once in a proof. That will happen. And then what? From step 3 to step 4, what did we do? Yeah, we divided, to go from step 3 to step 4, we divided by 4. What property allows us to divide the same thing on both sides? The division property. And I'm going to abbreviate that as well. I don't abbreviate subtraction property because subtraction abbreviation and substitution abbreviation are the same thing. Okay? And if you're not paying attention right now, you're putting yourself in a world of hurt. And I'm not going to lie, this unit is hard. And it's even harder if you don't pay attention. Okay? If you pay attention, by the end of it, it won't be so bad. Okay? But you gotta be focused and you gotta pay attention. You can't have those outside distractions, like your cell phone. You're putting yourself at a huge disadvantage if you are allowing your cell phone to distract you. So, what happened from step 4 to step 5? What changed? What happened? They flipped, right? What property allows us to flip? Yeah, the symmetric property. Negative 4 is equal to x. Using the symmetric property, we can then say x is equal to negative 4. We just switch them. Again, we don't really use this a ton. This is just an example of when we do. So take a look at example 2. Same kind of concept. All our steps are written out for us. We just have to state those reasons. So going from step 1 to step 2, what happened? Yeah, we distributed, so our reason's going to be distributive property. And again, I like to abbreviate. If you want to write out the whole thing, you can. But I like to abbreviate. Yeah, we distributed that 3 to get 6x minus 12 plus 4x equals 18. What happened from step 2 to step 3? We combine like terms. What property did we say allows us to combine like terms? The distributive property also allows us to combine like terms. So we use that. Okay. What happened from step 3 to step 4? Yeah, we used that addition property because we added the 12 on both sides. So to get step 4, we use the addition property. So I'm going to put add prop for addition property as my reason for step 4. And then what do we do from step 4 to step 5? We use the division property because we divided both sides by 10. Because whenever you combine like terms, because to go from 2 to 3, we combined this 4 and the 6 to get 10x. Whenever you combine like terms, you're also using the distributive. It's part of the adding is when you it's tricky. Adding is when you add the same thing on both sides. Here we only added the 4 on one side. We didn't add a 4x on that side, so that's why we can't use the addition. Good question. Other questions? So now we're going to do a full algebraic proof on our own. Okay? So we're going to do a step, write the result of that step, and then write the reason that allows us to do that step. So if we take a look at number 1, what do we have to do first to solve this equation? So we use the distributive property to get statement 2. So distributive property is going to be our reason, because that's what I used. Okay, and what do we get when we use the distributive property? 4 times 5x is 20x. 4 times negative 9 is 36 equals negative 2 times x, which is negative 2x, and negative 2 times 7 is 14. So use the distributive property to get that statement. What's going to be our next step to solve this equation? I heard addition. Yeah, we're going to add 2x to both sides using the addition property. So to get step 3, I use the addition property, so that's going to be my reason for step 3. And when I add 2x to both sides, I get 22x minus 36 equals negative 14. Does that cancel? What's our next step in solving for x? Addition property again, because we took the 36 and move it over to the other side. And again, to get step 4, I use the addition property. So I'm going to put that as my reason. And after I use the addition property, I get 22x is equal to 22. Negative 14 plus 36 is 22. And then what's our last step? What do we need to do? Use the division property because we're dividing 22 on both sides. So to get step 5, I use the division property. So that's going to go in step 5. And then when I divide by 22 on both sides, what do I get as my statement? Double check your math. Negative 14. Oh, yeah. And that gives you 1. So that's a basic flow of a proof. You go from each step, you do something, and you write down your reason for that step. Why you wrote that. Okay? These are just algebraic proofs to help you get into the flow by doing an actual geometric proof, which we're going to talk about next. Okay? So we're going to take a look at geometric proofs. Okay? We're not going to do a geometric proof today. We'll do one tomorrow, but we're just going to talk about the basics today. So a proof, definition, is a logical argument that shows a statement is true. You just can't say something and then everyone's just going to believe it. No, you have to argue why it's true. Okay? It's like in court. You have to argue why their innocence or their guiltiness. Okay? We use two column proofs in here. This is a two column proof. Okay? It's numbered statements. So we have statements with corresponding reasons. Okay? So they're numbered statements and corresponding reasons that show an argument in logical order. It has to be in logical order. So sometimes you have to write a certain step at a certain time. Okay? So essentially what you're doing is taking given information and you have to prove why it's true. Okay? And your statements are your argument why it's true, and your reasons are backing up that statement. Yes. Yes. Valid reasons for proof. Again, your reasons are backing up why you're arguing something is true. Okay, it's like your evidence. It's like when you cite something in a paper. Okay. Oh, I quoted this because it was in this text. Okay. That's kind of what reasons are. Okay. You can use definitions. You can say something is true based off its definition. Okay. You can use those properties of equality we just talked about. So addition property, subtraction property, transitive property, reflexive property. Those are allowed to be reasons in a proof. Okay. And you can use definitions, properties. You can use postulates, which we talked about at the beginning of the year, or in theorems. So definitions, properties, postulates, and theorems are reasons that you can use in a proof, reasons to back up your statements. We talked about postulates before, but just a refresher here at the bottom. Postulates are rules that are accepted true without proof. This is kind of a known fact. You don't really have to argue why it's true because it's just blatantly obvious that it is true. Okay? There's no argument for it. It is what it is. Theorems, those are rules that have been proven true. So there's something that someone said, like linear pair angles. They said linear pair angles add to 180. They had to then prove it to back it up. And we'll do that on Wednesday. Okay, we'll actually prove that theorem. But theorems are rules that have been proven true. So once you've proven them true, you can use them as a reason in other proofs. Okay. Questions over that? When we write proofs, we always write the given information first. So you're going to be given some sort of information. That always goes first in a proof, every time. Okay. The last statement in your proof will always be the proven statement. Okay, so you're going to be given information, and then you're going to say, based off this information, prove that this is true. And whatever you're trying to prove true is always last in proof, every time. Questions over that? Okay, so now what we're going to do is, these aren't proofs, but it's helping you get that basic pattern down for your proof. Okay? Once you get that pattern down, they're not that bad. Just getting the pattern down is kind of the tricky part. So this is something like you'll be given. You might be told that something is the midpoint of a line. That's going to happen when you do a proof. This is saying M is the midpoint of XY. So based on that info, you're going to have to conclude something. Okay, so start thinking about, well, what is a midpoint? Right? If M is the midpoint, that means it's directly in the middle. So if it's directly in the middle, what do we know about XM and YM? They're what? They're the same, right? They're congruent. So based off this given bit of information, I know that XM is congruent to YM. The reason why we knew that was just because we knew what a midpoint Right? So our reason is just basically definition of a midpoint. Because we knew, by knowing the definition of what a midpoint is, we knew that to be true. Right? And that's our reason that backs it up. Well, by definition, this is what a midpoint is. That's true. Okay? This happens a ton in geometry. A little helpful hint. Midpoint is a vocab word. Because that's definition, we learned about it. It was a vocab word in our notes. So whenever a vocab word pops up, your reason every single time is going to be definition of that vocab word. Okay? Little hint. You'll see that a ton. We'll see more examples, and it will make a little more sense down the road. What do we got here? We'll do one more. I think this is where we got one more from first period, and then we'll stop, and we'll do more of this tomorrow. So here, this is a piece of information we're given. We're given that DB, and this is a typo. I thought I fixed it. Bisects angle ABC. Okay? So start thinking. If I know DB bisects that angle, what can we make a statement? What do we know? What does an angle bisector do? Cuts it in half. So if this bisector is cutting this angle in half, what do I know about my two little angles? They're the same. So that's what we can say. We're like, well, if this is a bisector, then I know angle ADB is congruent to angle CDB. And bisects, that's a vocab word. So our reason's going to be definition of that vocab word. By knowing the definition of an angle bisector, I know this is true. So that's my reason. That's what backs up my argument. And I'm going to abbreviate definition. Definition of a, what type of bisector is this?
Angle bisector.
Angle bisector. So the definition of an angle, and I abbreviate angle bisector. Just by knowing what an angle bisector is, I know that those two angles are congruent. Questions over that? We'll do more of this